Everyone thinks math is just a tool. You learn formulas in school. You plug numbers into equations, you get answers. Done. Math is the language we use to describe reality, like English or Bangla or code. Useful, precise, but ultimately human-made. That's what most people think. Physics, on the other hand, feels real. Planets move. Light travels at 299,792,458 meters per second. Electrons have a charge of about 1/602 times 10 coulombs. Gravity pulls you toward Earth at 98 meters per second squared. Those are facts about the world and math. That's just the bookkeeping system we use to keep track of those facts. But wait. Here's the thing Richard Feynman kept hinting at over and over again. The relationship between math and physics is not like a dictionary translating words. It's not even like a measuring tape used to describe a table. It's deeper. Sometimes the equations know more than we do. Think about that for a second. Physicists write down equations to describe known phenomena. Then, years later, those same equations predict entirely new particles, new effects, new realities that no one has ever seen. And when we build experiments to check, the universe says, yes, the equation was right. How can that be? How can symbols on a page anticipate reality? Let me show you what I mean. Take Paul Dirac in 1928. He was trying to reconcile quantum mechanics with Einstein's special relativity. He wasn't chasing antimatter. He wasn't trying to invent science fiction. He was just trying to make the math consistent. He wrote down an equation. The Dirac equation, and when he solved it, something strange appeared. The equation didn't just describe the electron. It demanded another particle identical in mass but opposite in charge, a positive electron. No one had ever seen such a thing, but the math insisted. 4 years later, in 1932, Carl Anderson detected the positron in a cloud chamber. The equation had predicted antimatter before nature revealed it. Now ask yourself, was math merely a tool there, or was it a revealing structure that exists independently of us? Feynman loved this mystery. He often said that the unreasonable effectiveness of mathematics in physics is almost miraculous. But he didn't mean magical. He meant that the connection runs deeper than convenience. Math isn't just describing reality, it seems woven into it. So here's the question this video explores. What did Feynman really think about the relationship between math and physics? And why did he insist that equations are not just tools, but windows into how the universe actually works? Because if he's right, then when you write an equation, you're not just calculating, you're touching the structure of reality itself. Music fades in softly, let's rewind. To understand this relationship, we have to go back before Feynman. Start with Galileo in the early 1600s. He famously said that the book of nature is written in the language of mathematics. At the time, this was radical. Nature was thought to be qualitative. Heavy objects fall, light objects float. The heavens are perfect. Galileo changed the game by measuring. He rolled balls down inclined planes and found that the distance traveled was proportional to time squared, not approximately, precisely. That's math entering physics in a new way, not as decoration, as a structure. Then Newton arrived. In 1687, he published Principia. Inside were laws expressed mathematically, F equals ma. The gravitational force is proportional to the product of masses divided by distance squared. Notice something. The inverse square law was not obvious from daily experience. You don't feel gravity weakening as 1 over r squared, but the math worked. It predicted planetary orbits. It explained tides. It unified falling apples and the motion of the moon. Math wasn't summarizing physics, it was physics. Fast forward to James Clerk Maxwell in the 1860s. He writes down 4 equations describing electricity and magnetism. When he manipulates them, something surprising emerges. The equations predict waves traveling at a speed. That speed, about 300 million meters per second, the speed of light. Light, it turned out, is an electromagnetic wave. Here's what's astonishing. Maxwell didn't discover this by shining new light sources. He discovered it by trusting the equations. The math unified electricity, magnetism, and optics into one framework. Then Einstein entered in 1905. Special relativity begins with a simple postulate. The speed of light is constant in all inertial frames, but the consequences when expressed mathematically were staggering. Time dilation, length contraction, mass energy equivalence, E equals mc squared. That equation isn't just a shortcut. It encodes the fact that 1 kilogram of mass corresponds to about 9 times 10^16 joules of energy. That's the energy released by nuclear reactions. That's why stars shine. Again, math revealed what intuition could not. Now here's where Feynman steps in. By the 1940s, quantum mechanics was already successful. Schrödinger had his wave equation. Heisenberg had matrix mechanics. Dirac had unified quantum theory with relativity for electrons, but the theory was messy. Calculations were brutal. Predicting the behavior of electrons interacting with light required pages and pages of algebra. Feynman approached it differently. Instead of focusing on differential equations, he asked, what if particles don't take one path from A to B? What if they take all possible paths? This became the path integral formulation of quantum mechanics. Now here's where it gets weird. In Feynman's framework, to compute the probability of an electron going from point A to point B, you don't choose a single trajectory. You add up contributions from every conceivable path. Straight lines, curves, loops, wild zigzags, each path contributes a complex number. You sum them. The interference between them determines what you actually observe. Think about that. Reality doesn't choose one path and ignore the rest. It behaves as if it samples all possibilities and computes the result. That's not a metaphor, that's the equation. Let's pause. If Newton showed that math describes motion, and Maxwell showed that math predicts light, and Einstein showed that math reshapes time itself, Feynman showed that math governs even the invisible quantum behavior of particles. But here's the tension. Is math discovered or invented? If invented, why does it fit the universe so precisely? If discovered, where does it exist? Feynman had a pragmatic answer. He didn't obsess over metaphysics. He cared whether the equations worked, but he also recognized something deeper. He once said that the beauty of a theory lies in its mathematical structure. When an equation has the right symmetry, the right simplicity, it often turns out to be true. Symmetry, that's the key. Consider Noether's theorem, formulated by M.E. Noether in 1915. It states that every symmetry in nature corresponds to a conservation law. If the laws of physics don't change over time, energy is conserved. If they don't change across space, momentum is conserved. If they're invariant under rotation, angular momentum is conserved. One mathematical insight explains 3 physical principles. That's the 3 for 2 moment. One deep symmetry gives you multiple observable facts about the universe. So math isn't just a calculation device. It encodes symmetry, invariance, and structure. Now here's where it gets strange again. Why should the universe obey symmetry at all? Why should rotating an experiment 90 degrees not change its outcome? We experience symmetry in daily life. A ball thrown north behaves like one thrown east. but that everyday experience is grounded in a deep mathematical invariance. You don't see the symmetry, you see its consequences. Let's do a thought experiment. Imagine a universe where the laws of physics changed slightly every Tuesday. Gravity is 10% stronger on Wednesdays. The speed of light fluctuates randomly. Could stable atoms exist? Could stars form? Could you trust memory or causality? No. Consistency across time and space is what makes complexity possible. And that consistency is mathematical. When you use GPS on your phone, satellites orbiting at about 20,200 kilometers above Earth must account for both special and general relativity. Their onboard clocks tick slightly faster due to weaker gravity and slightly slower due to their speed of about 14,000 kilometers per hour. The net difference is about 38 microseconds per day. If engineers didn't correct for that using Einstein's equations, your location would drift by kilometers within hours. Every time you check directions, you are trusting the math of spacetime. That's not abstract philosophy, that's daily life. Now here's the deeper layer Feynman emphasized. Equations are not just summaries, they constrain what can exist. In quantum electrodynamics, the theory Feynman helped develop, the interaction between light and matter is described by precise mathematical terms. When you compute the electron's magnetic moment, the theory predicts it to astonishing precision. Measured value, approximately 231,930,436. Theoretical prediction, matches to more than 10 decimal places. That's agreement at the level of parts per trillion. Here, S what you'd expect. Maybe math approximates reality loosely, but that's not what happens. The agreement is so precise that it suggests the structure of the equation mirrors the structure of the world itself. Now, let me say that differently. It's not that equations fit experiments. Experiments reveal the equations. 1600, now here S where it gets beautiful. In the path integral picture, the classical world emerges from quantum mathematics. When you sum over all possible paths, wildly fluctuating contributions cancel out. Only paths near the classical trajectory reinforce each other. So Newton's laws appear not because they're fundamental, but because they're the dominant contribution in the quantum computation of reality. One mathematical framework explains both quantum randomness and classical determinism. Again, 3 for 2. One equation, multiple levels of reality. Think about what that implies. The solidity of your desk. The orbit of Earth around the Sun. The interference pattern in the double-slit experiment. All of it arises from the same mathematical core. Music swells softly, so what does this mean? If math is woven into physics this deeply, then doing physics is not just modeling the world. It's uncovering its architecture. When Feynman drew little diagrams to compute particle interactions, those diagrams weren't just bookkeeping tricks. They represented real processes, photons exchanged, probabilities calculated. The diagram is a picture of the equation. The equation is a picture of reality. Now step back. We started with the assumption that math is a tool, but the historical progression shows something else. Galileo measures and mathematizes motion. Newton unifies heaven and earth. Maxwell predicts light. Einstein reshapes time. Dirac predicts antimatter. Feynman reformulates quantum mechanics as a sum over histories. Each step deepens the entanglement between math and reality. Each equation doesn't just describe what we see, it expands what we can see. Implications. First, this changes how we think about knowledge. When we discover a new equation that works, we're not just inventing a clever model. We're uncovering constraints that reality must obey. Second, it reframes beauty in physics. Mathematicians often talk about elegance. Physicists too. The most successful theories tend to be mathematically simple and symmetric. Why should beauty correlate with truth? Feynman didn't claim to know why, but he noticed the pattern. The right equation often has a certain inevitability. Third, it suggests that the limits of mathematics might be the limits of physical possibility. If something cannot be made consistent mathematically, perhaps it cannot exist physically. That's a radical thought. It means that before building a machine or running an experiment, we can sometimes know what is impossible simply by examining equations. And here's the personal connection. When you learn math, you might feel like you're manipulating abstract symbols disconnected from life. But those symbols encode the same relationships that allow stars to burn for billions of years. The same relationships that let your phone triangulate your position. The same relationships that govern the chemistry in your brain right now. You're not just solving homework problems, you're rehearsing the language reality speaks. So let's bring it together. Feynman on math and physics wasn't saying equations are mystical. He was saying they are necessary. They are the compressed essence of physical truth. You can describe a wave in words, you can sketch it. But the equation captures its behavior across all conditions, all times, all places. It's like the DNA of a phenomenon. And as physics progresses, each new equation doesn't close the story, it opens it. Dirac's equation led to antimatter. Quantum electrodynamics led to precision tests of reality. Quantum field theory points toward deeper unifications. Each discovery builds on the previous one, amplifying it like an avalanche. One equation destabilizes old assumptions. That collapse triggers new insights. Those insights generate new mathematics. That mathematics predicts new phenomena, and the cascade continues. We started with the idea that math is just a tool, but Feynman's legacy suggests something more daring. Math is not merely how we describe reality. It is how reality is structured. And every time we uncover a new equation that works, we're not just calculating. We're listening more carefully to the avalanche as it builds, each discovery gathering momentum, carrying us forward, revealing that the universe was always deeper, more mathematical, more astonishing than we first imagined.